We are interested in designing molds for a variety of shapes. Our focus is on two-piece rigid molds where the mold pieces are separated by a cut plane. This type of mold is very useful for mass manufacturing, as seen for example in the production of chocolate bunnies. An object can be cast in a rigid mold if there is a translation so that the object can be removed from the mold without colliding with it. To construct this kind of mold, we need to find a valid cut plane, valid removal directions, and a valid cast mesh, which come together to make a mold. The removal direction does not necessarily need to be normal to the plane. We present a design tool for two-piece rigid molds. Starting with an input object, a user can design a shape that has a similar look and feel as the original, but can be cast using a two-piece rigid mold. It is not easy to make a general object castable. For this armadillo shape, the red regions would collide with the mold during removal. Simply editing the shape in a mesh editor and trying various cut planes and removal directions is a hard process, and it is difficult to arrive at a fabricable result. For two-piece rigid molds, where the mold pieces meet at a plane, there is a simple removability condition on the faces of a triangle mesh that determines if the mesh can be realized with a certain cut plane and certain removal directions. We leverage this condition to develop a design tool that allows for the generation of two-piece rigid molds from a wide variety of shapes, executing the large deformations that might be necessary. Designers can use it to explore a variety of different designs to make an input shape castable. The condition on triangle faces can be used to define a continuous castability energy. This energy can be optimized globally as well as locally to find the optimal cut plane and the optimal removal directions. To modify the shape itself, we use an as rigid as possible method to ensure that the features of the objects are preserved. The faces that would collide during removal are rotated out of the way. Some parts of the shape can be pinned to the cut plane during optimization. In this example, the user does not want the protrusions of the cross to be rotated out of the way, so they are pinned to the cut plane. Pinning different points to the cut plane allows the user to achieve very different results. For this hand shape, the user pinned two different sets of points, indicated by little blue dots on the right, resulting in two different castable result shapes. By pinning all kinds of points, the user can explore the design space. We use a heuristic based on the medial graph of a surface to suggest potential candidates for pinning to the user. If certain parts of the object are especially important to the user, they can be marked, and the tool will take great care to preserve them. In this example, the normal optimization distorted the eyes of the shape too much, so the user marked them as important. Here is an example of what the design process looks like. The user starts the tool and convinces themselves that the shape is not castable, no matter which cut plane or removal directions are chosen. The user then decides to let the tool pick the optimal cut plane and let it deform the shape to be castable. The user is unhappy about the way the tool deformed the horns and ears of the cow and decides to pin them, as well as some points in the body, to the cut plane during optimization. The tool then deforms the shape with these points pinned to the plane to achieve a fabricable result corresponding to the wishes of the designer. We used the tool on multiple shapes with different complexities to achieve castable designs. These designs were then cast using 3D printed molds. We even made gummy candy in one of our molds. In conclusion, we present a design tool for two-piece rigid molds starting from an arbitrary surface. Thank you for watching.